Hello, this is Dr. Hawkins again. Today I want to talk about specialty diodes. And if you have not already watched the podcast on rectifiers, I prefer that you watch this one first. They don't really depend directly on each other, but I may refer to things in this one that I've already talked about in that one and don't want to elaborate on again. So I would prefer that you watch the rectifier one first. I'm going to talk about, I don't know, 4 or 5 different ones. There's literally dozens of different types of specialty diodes. I'm just going to do a few here, a few of the more common ones. The first one I want to talk about is called a Zener diode. Let's see, we had a circuit we looked at in a previous podcast. Let's see if I can dig it up. Here it is. Where we're using a stack of 3 diodes to lock in a voltage across our load resistor. If the diodes weren't there, we'd have a voltage divider. We'd work a current and current times one resistor is its voltage, current times the other resistor is its voltage. Just a series circuit. Ignore this one for now. We would just have a series circuit. But having the diodes there in parallel with this load resistor lock this resistor voltage into 3 times 7/10 of a volt, or 2.1 volts. Now, using a Zener diode is a more elegant way of doing that. Let's see. A Zener diode looks like this. It's typically drawn in a shunt position, and its crossbar has some ears on it, if you will, that make it look sort of like a Z. I don't draw as well as the multi-sim program does, so I'll put that up in a minute. But something that I've drawn on it. But it has a breakdown voltage. Remember our first diode video, we talked about diode has 3 regions of operation. Let me put that in a different place. Still not what I want. One more time. There we go. At 7/10 of a volt, approximately, below 7/10 of a volt, I should say, we're in reverse bias. We're basically getting 0 current out, where this is current through the diode versus voltage across the diode. So if it's below 7/10 of a volt or negative, it's reverse bias and I get 0 current. But once I hit that 7/10 of a volt mark, it just takes off. This is called the forward bias region. And this is the reverse bias. Now, if we go far enough in the negative direction, we hit another break point that we call the breakdown of the diode. And it doesn't destroy the diode. Going into breakdown really doesn't hurt it as long as you don't put too much current. If you put enough current into it, in either direction, you can burn a diode up. But if we go into that breakdown region, we're really locking the voltage in at whatever this breakdown voltage is. And you can get Zener diodes that have pretty much any breakdown you want to. For smaller voltages, I think they go in steps of like 0.1 volt. You can get like 0.1, 0.2, 0.3, 0.4, 1.5, 1.6, 2.7, 2.8, and up to a point of about 10 volts or so, it may start going in a little bit bigger steps like 10.2, 10.4, and so on. But you can get virtually any breakdown voltage that you want. And what that does is, once again, just like on the previous page where I use a stack of 3 rectifier diodes to lock in 2.1 volts to a load resistor, whatever voltage I want to choose, I have to buy a diode that has the voltage I want to use. I can't use one diode and get different voltages. But if I know what voltage I want, I can purchase a diode that has something very close to that voltage. So let's look at an example of how that would look in a circuit. Alright, I have a Zener diode, and if you look close, that's a little smaller than I intended. I'm not sure if I can make it any bigger or not. Let's see if there's a way to do that. Yeah. You can see there's some like a little, on the crossbar, it has some little ears on it that make it look sort of like a Z for Zener. And in this case, I've chosen a diode that has a breakdown voltage of 15 volts. And that's because, just like with the previous circuit, I may have this in a circuit where I need, where I need 20 volts going out to some other parts of the circuit. So that's why I have a 20 volt supply. But I also need 15 volts for some part of the circuit. And this load resistor here is representing, it could be a lot more complicated than just a resistor. Typically it is, but for learning circuits, we tend to use just a load resistor to model more complicated circuits. So anyway, when we used the rectifier diodes in a stack, we had to determine, we had some conditions we had to meet in order to determine if the diode was forward biased or not. And it's similar here with the Zener diode. There's some conditions we have to meet to determine whether or not the diode is in breakdown or not, or just simply reverse biased. Move that over there where I have a little more room. We can just lose that. All right, first condition, let's just do them down here in one, enough voltage. We'll call it VZ for Zener. All right, the current has to be in the right direction, which is pointing opposite the direction of the diode. Current needs to be going this way to go into breakdown. We call that ID. We call it IZ because I'm going to do that something with it later. IZ has to be in the reverse direction. 3, it has to be a completed circuit. So you see those. This is very similar to the conditions that we had to determine if a diode's forward biased. It's just the direction of the current's reversed, and instead of the 7/10 of a volt, we have to have more than whatever the breakdown voltage of the diode is. Now there is a fourth condition. You have to have an IZ. Now there can be a condition where this is false, even if the other three are true. This is true if IS is greater than IL. My diode current then is going to be, and that has to be positive in the direction I've got it drawn, which is backwards to the direction of the diode arrow. So if the resistors are not set properly, there can be a condition where those two are either equal or trying to make the load current bigger than the supply current. Either one of those cases, I'm not going to have any diode current. And in that case, I failed the fourth test, and the diode does not go into breakdown. You just have it be reverse biased, and the circuit will just act like a series circuit voltage divider. Let's work out the example here. We'll have another copy of the drawing. Up here in the corner out of the way. All right. The first test was, is there enough voltage? And we have 20 volts in the supply. We only need 15 for the diode, so we meet the first test. The second test is the current going in the proper direction to reverse bias the diode? Now again, I'm going to have a supply current coming out that way. When I get to this junction, it's going to split. And part of it's going to go that way. That's my diode current. So then we have one. And the rest of it's going to go to the load. So we meet the second test. The current's going in the right direction to reverse bias the diode. That's supposed to be an I there, not a T. All right. The third test is there a completed circuit. Yes, the grounds are all connected together, so we meet 3. Now the fourth test, we don't know yet. So what we do is assume not saturation, that's the transistors. I get those. I think I may have got that mixed up on a previous video. I apologize if I did. The proper term here is breakdown. We will deal with transistors next, and they have something we call saturation, which is similar, but it's not exactly the same thing. So here we're dealing with breakdown. All right, we assume we're in breakdown. So that means the diode's dropping 15 volts. That means the voltage across R1 has to be 15 volts. That's the whole purpose of the diode. Since they're in parallel, the diode forces the resistor to draw or to drop 15 volts. Should be R load really, but I left it R1 on that one. That's okay. So that means by Kirchhoff's voltage law, the voltage across RS, the supply resistor we're calling it, that's what the S stands for, is the supply voltage minus the diode voltage. And in this case, that'll be 5 volts. So that gives me my supply current will be VRS over RS. Volts over 100 ohms. Or 50 milliamps. My load current is my Zener voltage. It's my resistor voltage, but it's the same as the Zener voltage. $15 over 1,000. 15 milliamps. So our assumption that the source supply current is bigger than the load current is true, and that means we've met the fourth condition, and we are in breakdown, and the work we've done so far is correct. Now, I'll do an example in just a second where that's not true. I'll just go ahead and finish this first. I'm just right there at the end here. All that's left to calculate now is the diode current. So that's 50 minus 15. Okay, now let's look at an example where that doesn't work out. Same circuit, except now I want to change the supply resistor. Instead of 100 ohms, just make it 500 ohms. Now we make the same assumptions. We still got the same, everything still works out through the first three conditions, just exactly the same as we did in the previous example. We go ahead and make the assumption of number 4, that the supply current's bigger than the load current, which leaves me some current to go into the diode. So we're assuming, once again, and the voltage is still going to be the same with that assumption. Now, with that assumption, the voltages are going to be the same. VRS is still going to be 5 volts. Not I. Not yet, anyway. Now let's calculate the currents and see if our assumption is correct. IS now is going to be VRS, just like before, but it's a different resistor. Let's see. It's only gives me 10 milliamps as opposed to the 50 we had before. And IL is still 15 volts over 1K. So now our assumption is not true. If you try to subtract them, that would say that the diode has a negative current. And that can't happen here. So not in saturation. What do we do in this situation? Well, we just treat it as a series resistor circuit. So the diode is reverse biased. And it's just like I have 20 volts, 500 ohms, and 1K all in series. And you know how to work that problem. You find total resistance, divide into the voltage to get the one and only current in a series circuit. And then multiply that current times the two resistances to get their voltages. And they have to add up to equal the supply. Enough about Zeniths for now. Let's look at a couple of other different types of specialty diodes. Let's see, the first one I want to talk about is called a varactor diode. And actually, once again, I think I want to stop the video here to keep it from going too long and break it into one more video.